Alright, so in the last video we introduced an algorithm for solving matrix equations. So equations of the form A times X equals B, where unlike in section 6.1, these matrices X and B are allowed to have more than one column, right? We know that if you have a single column, you're just dealing with a system of equations. When you have many columns, you basically are dealing with many systems of equations, but each one of those systems has this same coefficient matrix A. And so we went over the fact that if I want to solve for X in something like this, as long as A is a square matrix, then what we should do is we should do A on the left and B on the right, like so, an augmented matrix where there's multiple columns to the right of the bar, and see if we can reduce this down to, well, the reduced row echelon form of A, and hopefully the solution will be over there on the right. It depends on what we get for our reduced row echelon form. Okay, so let's try this in this particular case, right? So now X here, right? X might look like say X1, X2, X3, X4, and notice that if I were to actually work out A times X, if we wanted to do it, I'm going to get 3x1 minus 2x3, and then 2x1 plus 4x3 as the first column, and the second column is the same thing but with the variables x2 and x4, so I get 3x2 minus 2x4, 2x2 plus 4x4, right? And then of course this guy here, well, that would be equal to 2, this guy should be equal to 0, this guy should be equal to 1, this guy should give me minus 3, right? And so if you only looked at one column at a time, you can see that if I just looked at this part here, right, then I am dealing with a system of two equations and two unknowns, and I would solve and I would have this coefficient matrix A. Similarly, if I was dealing with this part, again, two equations with two unknowns, but same coefficient matrix. What changes is the constants on the right-hand side. So following the procedure, we write down A, and then we write down B, and we try to reduce our echelon form, right? And we know that when we're trying to get to reduce our echelon form, we look at these numbers over here on the left. So that's why this is going to work. It's because we do the same row operations for both this column and this column because it's the same numbers on the left in both cases. First thing we need to do is create a leading 1. In this case, I think the easiest way to create my leading 1 is going to be to do 3 minus 2. So I'm going to do row 1 minus 2 row 2. Make that my new row 1. So 3 minus 2 gives me 1, minus 2 minus 4, minus 6. 2 minus 1 is 1, 0 minus minus 3 gives me a 3, and then we recopy 1 minus 3, there we go. So the next thing I'm going to do is I'm going to do row 2 minus 2 row 1 because I want to create my 0, right? So that's going to be my new row 2. So 1 minus 6, 1, 3, 0. This is going to be 16. 1 minus 2 minus 1 minus 3 minus 6 minus 9. Alright, and at this point, to get that second leading 1, there's only one choice. I've got to divide by 16. So 1 over 16 row 2 will be my new row 2. 1 minus 6, 1, 3, 0, 1. Minus 1 over 16 minus 9 over 16. And one last row operation to get this into reduced row echelon form. I've got to do row 1 plus 6 row 2. And that's going to be my new row 1. So I get my identity matrix here on the left, which is what I want if I'm looking for a unique solution. That's exactly what I'm looking for. And what do I get over here? Here I got to do a little bit of fraction arithmetic, right? So 1 plus 6 times minus, so I got 1 minus 6 over 16. So I can reduce the 6 over 16, that's going to be 3/8, so it's 8 over 8 minus 3 over 8. I get 5 over 8 in that spot. The other one I've got 3 minus 6 times 9 over 16. Again, I can reduce that down to eighths, so I've got, so 3 is 24 over 8, and then, so cancel that, that's 8. 3 times 9 is 27 over 8, so 24 minus 27, I get minus 3 over 8, and then minus 1 over 16, minus 9 over 16. Okay, so my algorithm says that if I reduce down and I get the identity on the left here, then whatever I have on the right, that's the matrix I'm looking for. Okay, that's my X. So my conclusion here is that X should be this guy. 5 over 8 minus 3 over 8 minus 1 over 16 minus 9 over 16. And of course we could check, if we wanted to check, so A times X, so I do my A 3 minus 2, 2, 4, X 5 over 8 minus 3 over 8 minus 1 over 16 minus 9 over 16. And alright, there's a bit of, fraction arithmetic here. It's going to get a little bit messy. When I do the first row times the first column, 3 times 5/8, I've got 15/8. 2 minus 2 times minus 1 over 6, that's 1 more, 1 over 8, right? 2 over 16 is 1 over 8. 15 over 8 plus 1 over 8 gives me 16 over 8. 16 over 8 is 2. If I do row 1, column 2, 3 times minus 3 over 8 minus 2 times minus 9 over 16. So that's minus 9 over 8 plus 9 over 8, 0. Now I do row 2, column 1, 2 times 5/8, that's 5 quarters. 4 times minus 1 over 16, that's minus 1 quarter. So 5 quarters minus 1 quarter gives me 4 quarters, which is a 1. And finally, row 2, column 2, 2 times minus 3/8. So minus 3 quarters minus 9 quarters, that's minus 12 over 4. Minus 12 over 4 gives me minus 3, which is what I want. So it worked in this case. And just to make sure that wasn't a fluke, we'll try one more example. Alright, remember that I can put any number of columns I want for this matrix B, so let's try it with 3 columns and we'll see how it goes. So I set things up. 0, 0, 1, 2. Okay, so I've got my leading 1. I'm going to do row 2 plus 2 row 1 and make that my new row 2 to create a 0. And let's recopy. Here we see that something interesting happens. We run into a bit of trouble. 0, 0. Okay, what happens over here? 6 minus 6, I get a 0, 0, and 4. Okay. So here's a case where we actually cannot solve. This is in reduced row echelon form, right? And so if I were solving here, right, what I would be trying to solve is A times X. Oops. So my A times X would be A times, so X would look like X1, X2, X3. Each of these is a 2 by 1 column, and remember that's AX1, AX2, 2, AX3, and so we can solve this guy. We can solve A times x1 equals the first column, 3 minus 6, and we can solve A times x2 equals to 0, 0, but if even one of the columns doesn't work and the third one doesn't, this guy is inconsistent. Why? Because if I kind of ignore these guys, right, ignore those and just think about that last column, right, what does the bottom row in that in this matrix say? It says that 0, 0x plus 0y equals 4. 0 is not equal to 4, so there is no solution, right? So the third column gives us an inconsistent system, and if even one of the columns fails, the whole thing fails, and so there is no solution in this case. All right, so this is the idea for solving sort of multiple systems at once when each one of the systems has the same coefficient matrix. Same idea as before. You set up your augmented matrix and reduce. It's just that now you have multiple columns over on the right. So in the next few videos we'll see how to put this to use in order to compute inverses of a matrix.